Okay, now let us look at another example. Here it is said if an input that is given by x of n, which is equal to 1 for all time, is given to the system with the frequency response that we have found earlier, h of omega to be equal to 1 over 1 minus 0.8 e to the power minus j omega. Then our task is to find y of n. Fair enough. Okay, now let's go on to the solution. Here, say the input given x of n is equal to 1. Now, if we write 1 as 1 raised to the power of n, it is quite mathematically logical, because 1 raised to the power of anything will result to 1 as well. So now this can be further written as e to the power of j dot 0, that is j times 0 whole raised to the power of n. This is also true because e to the power of j times 0 is e to the power of 0, which equals 1, and 1 raised to the power of n is also equal to 1. So if that is the case, so what we can deduct from this statement is that 1, the number 1 is a complex exponential with a frequency omega equal to 0. Is it not? Because this is our value of omega, which is 0 in this case. So 1 will be a complex exponential with a frequency value omega equal to 0. And for that very reason, if we work with any DC quantities, we can easily say that the frequency of a DC quantity will be 0, and this comes from the expression over here. So now, since we got the frequency value to be equal to 0, we need to find the amplitude response of h of omega and the phase response of h of omega. Very well then. So the amplitude response of h of omega, where omega in our case is 0, so the amplitude response of this value will be equal to 1 over 1 minus 0.8 e to the power minus j times 0 and its magnitude. So this can be simplified, 1 over 1 minus 0.8 and further 1 over 0.2, which is nothing but 5. And the magnitude of 5 is equal to 5 since it has not got any imaginary part. So that is our required amplitude spectrum or amplitude response. Now let us move on to the phase response. So we can write angle of h of omega, omega in our case being 0, so h of 0 is equal to angle of 1 over 1 minus 0.8. Fair enough. So this will be 1 over 0.2's angle and consequently angle of 5. So angle of 5 will be 0 because 5 can be written as 5 plus j 0, and any complex number given in the form as a plus jb will have an angle to be equal to tan inverse b by a. So in this case the angle will be tan inverse 0 by 5, which is tan inverse of 0, and obviously tan inverse 0 is 0. This is where the phase response comes for any DC value. So now, as we have seen earlier, the output y of n can be written in terms of the amplitude response and consequently the phase response. And the structure will be something y of n to be equal to the amplitude response times y of n plus the phase response. So this is our generalized structure that we have derived in the previous video. So simply y of n can be written y of n is equal to the amplitude response is 5 1 raised to the power of n plus the phase response, which is 0. So this is equal to 5 times 1 raised to the n, which is equal to 5. And it is true for all values of n. So another way of perceiving it is that the system has a DC gain of 5. There is an input of 1 gives us the output equal to 5. So if we give the system an input of 1, the transfer function is designed in such a way that the output, whatever may be the case, will be multiplied by 5. So if it is 1, this will give 5, 2, this will give 10, and so on. So I hope you understand the problem. In this problem, we tried to look upon find the output given for a frequency response of a system. So let us move on to another problem. Okay, now in this example, for the same transfer function, h of omega is equal to 1 over 1 minus 0.8 e raised to the power of minus j omega. We are to determine y of n for the given input, x of n, which is equal to cosine of pi by 6 n minus 0.4. Okay, so let us go into the solution. Like the previous problem, our task first of all is to find the angular frequency of the input. So here x of n is clearly in the form cosine of omega n, plus theta, where theta is any arbitrary phase shift, n being the time operator, and omega being our frequency. So from this analogy, we can write our omega to be equal to pi over 6. So now our second task is to find the amplitude and the phase response. So magnitude of h of pi by 6 is equal to 1 over 1 minus 0.8 e raised to the power of minus j, omega being pi by 6, and its magnitude. So this will be equal to 1 over 1 minus 0.69 j 0.4. You can very well calculate it using the... So this value can be easily derived if we expand the exponent in terms of the Euler series. This is a real part, the cosine angle, and this is the sine angle, or rather the sine ratio. So this will give us a value of 1.983. Okay, so this is our magnitude or amplitude response, and consequently the phase response h of pi by 6 will be equal to angle of 1, as I've said, the angle of the numerator subtracted minus the angle of the denominator, 0.8 e to the power minus j pi by 6. This will be equal to minus 0.916 radians. So once again, you can easily calculate, just decompose this e term using the Euler's relation. So once again, we found out our amplitude response and the phase response. So we can easily write our output y of n to be equal to our amplitude response 1.983 and our input function cosine of pi by 6 n minus 0.4, and the phase response will be added over here. So this is minus 0.916. So this is our required output value. You can simplify, just add these two terms up, and if you keep the result up to this, no problem at that. Okay, let us look at another example. Here, let us consider a continuous function. Say the input is given as x of t to be equal to cosine of 1500t. So we cannot operate a continuous input in a discrete system. So in order to make the system discrete, there must be some sampling period present. So in our case, the sampling period which is Ts, is 0.001, that is 1 millisecond. Our task is to find y of n, the transfer function being the same as this one. So go to the solution. So x of t is given. Now if we are to convert it to x of n, what we need to do is simply replace this t with n, capital Ts. So this will become cosine of 1500 nts, and ts in our case being 1 millisecond when multiplied by 1500 will become cosine of 1.5 n. So this is our required input, and from this function it is clearly visible to us our frequency omega is equal to 1.5. So once again we do the same thing, determine the magnitude response, which is equal to 1 minus 0.8 e raised to the power minus j 1.5 whole inverse. This magnitude will be equal to 0.809. Do the calculation by yourself, and the phase response h of 1.5 is equal to 0.02 radians. The calculation is also left to you. So finally, the output y of n can be given as 0.809 cosine of 1.5 n minus 0.702. So enough mathematical problems. Let us move on to some theory portion. So let us establish a relationship between the frequency response of a system with the pole and 0 of the transfer function. So let us say a transfer function h of z can be written in the form k times z minus zi, this is z1, z minus z2, and this goes to z minus zn, and this is z minus gamma 1, z minus gamma 2, and so z minus gamma n. So evidently a transfer function given in the form, as we have learned from the z transform, z of I and gamma of I will be our zeros, and this will be the poles of the system. So now let us replace z is equal to e to the power of j omega, which essentially means that we are evaluating h of z on the unit circle. So if z is equal to e to the power of j omega, all the points that will occur in the frequency domain will be on the unit circle. Say for omega is equal to 0, 1, 2, 3, 4, 5, 6, any values of omega up to 360, it will be on the unit circle. So replace z by e to the power j omega. The equation given over here becomes h of e to the power of j omega, or simply h of omega is equal to k. This k is an arbitrary constant values. It may or may not be present. So this becomes e to the j omega minus z1, e to the j omega minus z2, and consequently e to the j omega minus zn. Similarly, in the poles, this will become e to the j omega minus gamma 1, e to the j omega minus gamma 2, e to the j omega minus gamma n. So, from this quantity, let us come to some points. The quantity e to the power of j omega is a point on the unit circle. This I have said earlier. And the quantity e to the power of j omega minus zi is a vector from zi to e to the j omega. So this term e to the power of j omega minus zi, say the system has two zeros at this point and this point, and this is our e to the j omega. Omega will be having a value. So this term essentially dictates the vector that extends from this to over here and this over here. And this is also the case if omega has a different value. Say at this point the vectors will be from here and to here. So this is simply our vectors, and you have guessed it already, e to the j omega minus gamma I is the vector from gamma I to e to the j omega. So if the system has two poles, these are our zeros. If the system has two poles, say over here and here, and this is our e to the j omega value, so the vector will be this, and this is the vector values. So these are some of the realizations that we get. So now, using the polar coordinates, we can write Ri e to the power of j phi I is equal to e to the j omega minus zi for the values numerator. E to the power j omega is a complex quantity and zi is any constant value, so the result will be a complex quantity. It is quite evident, and so this complex quantity can be written in the polar form as shown over here, where I have said Ri being the magnitude and phi I being the phase. Similarly, for the denominator, we can write di e to the power of j theta I is equal to e to the power of j omega minus gamma I for the denominator. So simply we replace these values in h of omega, we get is equal to k R1, R2, this goes to Rn, d1, d2, this goes to d of n, and e to the power j phi1, phi2, phi minus theta 1, theta 2, and theta n. So what we have done is, so this value is replaced by R1 times e to the j phi of 1. So let me write it down for a better explanation. So this becomes R1 e to the j phi 1. This becomes similarly R2 e to the j phi 2, and so on. So this becomes d1 e to the j e to the j, sorry, this becomes e to the j theta 1, and so and so. So if that is the case, now these are constant values multiplied throughout up to n. So what we did is simply taken this geometric series of r and separated it using in the numerator, and similarly we did the same case for the denominators, and for all this exponential term divided by a different type of exponential terms, these are written as e to the power of j, okay, no, before that, these exponential terms are multiplied and all its indices are added. So this we get j times j taken as common, phi 1 plus phi 2 plus phi 3, and so, which goes to phi of n. This is for the numerator. Similarly, we do the same thing for the denominator. This will be theta 1, theta 2, and so, it goes to theta of n. So what this essentially means is that there will be two exponents in the, one in the numerator, one in the denominator. So if we divide two exponents, their powers get negated, and there will be this term j times the power of the numerator minus the indices of the denominator, and this will be the new index of the exponent. I hope this is clear. So let me give a different bracket over here, because this j is multiplied to both the numerator and the denominator. So now let us look at the amplitude response and amplitude response. And in doing so, we shall learn about why we have taken h of omega in this form. So h of omega, in case of the amplitude response, will only have k r1 times r2 r of n divided by d1 times d2 d of n. So this can be simply written as the product of distance of zeros to e to the j omega divided by product of distance of poles to e to the j omega. Otherwise, h of omega can be written as k times capital pi, that is a running multiplication where I goes from 0 to n, Ri divided by capital pi, that is the running multiplication where I goes from 1 to n, di. Now the benefit of this form is that if we are given a pole zero plot, say this is our pole zero plot in the z domain, this is the unit circle, this is Re of z, this is Im of z, that is the real z, and this is the imaginary z. So what we can do is simply determine the distance for all the poles and say the distance from all the zeros. So just multiply the distance for all the poles and multiply the distance for all the zeros and divide one another, and in this fashion you can simply derive the amplitude response if a pole zero plot is given to you. This becomes much easier that way. Okay, now let us move on to the frequency response. So for the phase response, angle of h of omega can be written as phi1 plus phi2 plus phi(n) minus theta 1 plus theta 2 theta n, which is nothing but the sum of the zero angles that is formed by e to the j omega, and this is nothing but the pole angles that is formed by e to the j omega. So simply if we can determine the angles between the zeros and the poles, we can subtract it one from one another, and through the subtraction we can easily determine the phase response. Point to be noted: all this thing comes or boils down to a single summary, that is the amplitude and phase response of a system is essentially governed by the number of poles and zeros, which is quite evident because if the number of poles are different, say there is a lesser number of poles or lesser number of zeros, this angle of h of omega will not be same if there is any value of phi absent or any value of theta absent. So the crux or the cream is that the amplitude and the phase response of a system, rather I should say an LTI discrete system, is governed by the number of poles and zeros. And this is the case for our filter as well, because as we have established, the digital filters are nothing but LTI systems. Okay, enough until now. In the next video we shall look upon some of the examples how the pole and zero changes the frequency response.